What specific problem does your proposed method aim to solve in the context of explaining model parameters for clustering and classification?
The proposed method aims to solve the problem of interpretability in model parameters for clustering and classification tasks. Traditional models often learn high-dimensional parameters that are difficult for humans to interpret, leading to challenges in understanding the underlying categories or features represented by these parameters. By introducing a family of models that utilize natural language predicates as parameters, the method allows for the extraction of 0/1 features that are inherently interpretable. This approach not only enhances the explainability of the learned clusters or classifications, but also enables the models to recover ground truth predicates effectively, as demonstrated through various statistical modeling problems and datasets. Ultimately, the method seeks to bridge the gap between complex data patterns and human understanding by providing clear natural language explanations for the model's behavior.
Can you explain how the proposed method works? Illustrate it step by step, including details on continuous relaxation and the iterative refinement process.
The proposed method operates through a structured framework that consists of 3 core components: optimizing weights, relaxing predicates, and discretizing them. First, the method initializes continuous predicates, (phi), and optimizes the weights, w, using the function textOpW, which assigns each text sample to the cluster with the highest likelihood. Next, it employs textOptRelaxedPhi to create a continuous relaxation of the discrete predicates, allowing for gradient-based optimization of the loss function, L. This continuous representation is then used to generate candidate predicates through the textDiscretize function, which prompts a language model to produce natural language predicates that explain the data. The iterative refinement process involves repeatedly identifying the least useful predicate, optimizing its continuous representation, and updating it with a new candidate predicate, thereby enhancing the model's performance over multiple iterations. This combination of continuous relaxation and iterative refinement allows the method to effectively recover interpretable predicates that explain complex datasets.
Could you provide a simple yet illustrative example of how your method operates, using specific predicates and describing the steps involved in processing a text sample?
To illustrate how our method operates, consider the predicate discusses the U.S. election. The process begins by extracting a feature vector from a text sample. Say, what are the latest updates on the U.S. election? We prompt a language model to evaluate whether this predicate is true for the sample, resulting in a binary output, 1 if true, 0 otherwise. Next, we optimize the continuous relaxation of the predicate, denoted as (phi), using gradient descent to maximize the log likelihood of the data. After this, we discretize (phi) back into a natural language predicate by generating candidate predicates and selecting the one that best explains the sample's features. This iterative process allows us to refine the predicates, ensuring they accurately capture the underlying data patterns while remaining interpretable.
What are the theoretical or practical benefits of using your method in terms of interpretability, efficiency, or performance compared to existing models like LDA or BER topic?
Our method offers significant theoretical and practical benefits in terms of interpretability, efficiency, and performance compared to existing models like LDA and BER topic. Firstly, by parameterizing model features with natural language predicates, our approach enhances interpretability, allowing users to understand the underlying concepts directly, unlike LDA or BER topic, which rely on high-dimensional parameters that are often difficult to interpret. Secondly, our optimization algorithm, which employs continuous relaxation and iterative refinement, demonstrates improved efficiency in learning predicates, achieving a 2% increase in F1 score compared to specialized methods for explainable clustering, thus enhancing performance across various tasks. Additionally, our model-agnostic framework is versatile, applicable to clustering, classification, and time series modeling, making it more adaptable than traditional models that are often limited to specific tasks. Finally, our method effectively utilizes temporal correlations in time series data, outperforming shuffled datasets, which indicates a deeper understanding of the data dynamics compared to static models like LDA.
How did you validate the effectiveness of the proposed method? Describe the experimental setup, datasets used, and the metrics employed for evaluation.
To validate the effectiveness of our proposed method, we conducted experiments using a suite of datasets specifically designed for 3 statistical models: clustering, multi-class classification, and time series modeling. We utilized 5 datasets for clustering: Agnew's, DBpedia, NYT, Bills, and Wiki, a classification dataset with 5,000 articles across 20 classes, and a synthesized time series dataset derived from the NYT articles. The evaluation metrics included F1 score and surface similarity, where we matched learned predicates with reference predicates to compute the F1 score and assessed the semantic similarity of predicates using a language model. Our experimental setup involved generating candidate predicates using GPT-3.5 Turbo, denoting predicates with Flan T5XL, and creating embeddings with the instructor XL model, averaging performance across 5 random seeds to ensure robustness. The results consistently demonstrated that our method outperformed naive approaches and matched or exceeded the performance of specialized methods for explainable clustering.
What limitations or drawbacks have you identified for your proposed method, and how do you plan to address them in future work?
The paper does not explicitly outline limitations or drawbacks of the proposed method. However, it implies challenges related to the optimization of discrete predicates, as they do not allow for gradient-based optimization. This limitation necessitates the use of continuous relaxation and iterative refinement, which, while effective, may not fully capture the complexity of all datasets. Additionally, the reliance on language models for generating candidate predicates could introduce biases or inaccuracies in the explanations provided. Future work could focus on enhancing the robustness of the predicate generation process, possibly by integrating more diverse sources of information or refining the optimization techniques to better handle the discrete nature of predicates. Furthermore, exploring the scalability of the method across larger and more complex datasets could also be a valuable direction for future research.